Good evening. I'd like to welcome everyone to Kahn Auditorium for tonight's event, CIERA's 10th annual public lecture. I'm Jay Walsh. I'm the Vice President for Research here at Northwestern. And tonight's event, as most of you know, is brought by the Center for Interdisciplinary Exploration and Research in Astrophysics, otherwise known for most of us as CIERA. I don't know about you, but DNA is a nice word. You know, some of you might even know what it means, deoxyribonucleic acid. Nobody goes around talking about that, so we're just going to say CIERA. We are not going to say the Center for Interdisciplinary Exploration and Research in Astrophysics. Vicky, did you come up with that name? So, that was a no from the backstage for those of you. She wanted to have a literate CIERA. Science, every year does a breakthrough of the year. For those of you who can see this, it's a depiction of two astronomical bodies, happens to be neutron stars, that are combining and producing light, actually gamma rays probably. And if you go inside, this is the breakthrough of the year. Last year. You see a quote. But the merger also poses puzzles that have whetted astrophysics' appetites for more data. The gamma ray burst was surprisingly feeble, says Vicky Kalogera, an astrophysicist and LIGO team member at Northwestern University in Evanston, Illinois. It is our delight tonight to have the author of that quote stand here and talk about the work that she does, including the breakthrough of the year. But a little background. CIERA was founded about a decade ago here at Northwestern, and it was established as an interaction across the entire campus for innovative research in the field of astrophysics, but it pulls together all sorts of groups. It includes more than 60 faculty from, now I'm going to read, computer science, applied math, statistics, biology, chemistry, planetary science, electrical engineering, material science, mechanical engineering, and obstetrics and gynecology. Stars give birth to lots of things. It's an all-star group here. I'll stop at the puns. So the annual public lecture serves as CIERA's premier public outreach event. For those of you who've been here before, previous speakers have included incredible luminaries. One who was here just the other day in town, Neil deGrasse Tyson, also gave a talk here 3-4 years ago, something like that. You can learn about CIERA online. I'll let you find that at CIERAnorthwestern.edu. But before introducing Vicky, I'm going to say a few things about some special guests. First of all, we have guests from CIERA's Board of Visitors here. So maybe just wave your hand if I say your name and you're here. Diane Blanco. Very good. Zach and Aaron Sidwell. Zach, I know you're here. Thank you. Don McMillan. Bert Fujishima. Payson Weil. And Judith Pierpoint. Is Judith here yet? Not yet. Okay. So Vicky has put together a really great group of Board of Visitors, and we're very grateful for the support that they provide for CIERA, from our luminary speaker today through the ranks of assistant professors, associate professors, junior folks, the postdocs and the grad students. I also want to acknowledge a few other guests. My boss, Morty Shapiro, is here somewhere, the president of the university, and also perhaps Teresa Woodruff is here. She's the dean of the graduate school and the OBGYN member of CIERA, just so you know. And lastly, I should announce that for those of you who are here for Alumni Weekend, this is homecoming weekend, and maybe a few good things will happen for all the alums who are back for that weekend. So Couple things. Vicky is the Daniel I. Linzer Distinguished Professor in the Department of Physics and Astronomy. She's also the director of CIERA. She's a newly elected member of the National Academy of Sciences. This is a really signature event in the life of a scientist. And she serves, as the quote sort of indicated, as one of the leading astrophysicists on a very large collaboration called the Laser Interferometric Gravitational Wave Observatory, otherwise known as LIGO, that scientific collaboration. In her role at LIGO, she's one of, as I sort of mentioned, the top physicists, top 3 is named here, who took the stage at the National Press Conference in October last year to announce the first ever detection of the collision between the 2 neutron stars, which is why this ended up on the front page of Science. Vicky has many, many awards and honors. I'm not going to go through all that. You can find that online. With that, I will announce our speaker tonight, Vicky Kalogera.
Hi, everybody. Mic is on. I can hear it. Thank you all for being here. Thank you for coming. It's a great pleasure to welcome you tonight. Welcome our president, whom I saw, but I can't see here. There he is. And of course, thank you, Jay, for the kind introduction. Welcome to our Northwestern faculty, students, undergraduates, graduate students, CIERA, and other researchers across the university. Welcome to alumni. We're opening the series of public events for the homecoming weekend. And of course, welcome to the members of the local community within which we get to thrive and pursue our goals within the university and inside this wonderful local community. I can't believe that you're here joining us to celebrate this 10th anniversary of CIERA. As far as I'm concerned, in my own head, I'm a young, energetic faculty who just arrived on campus, trying to figure out my way around campus, both physically and metaphorically. Thankfully, I think I'm still energetic. Morty will tell you that. Maybe not so young, and I'm no longer figuring out my way around campus, both metaphorically and physically, but I'm still definitely figuring out my way around the world and often around the universe. So for today, what I would like to do is to try and give you first a bit of a flavor of what CIERA is. It will be impossible to really tell you about all the things we have had the pleasure of experiencing through the past 10 years. The thrill of discoveries, the excitement of achievement that I have certainly experienced through my colleagues, through the young students and postdocs, and faculty colleagues and young faculty that we have recruited. So I'll try, oops, my slides are not exactly, why are we in this mode? That you can see my other slides. You're not supposed to see my other slides. I've never seen this mode of presentation. There we go. Okay. Hopefully they were too small for you to see. Where was I saying now? Yes, so I'm gonna try and give you a big picture of what CIERA is about, and then I will try to give you, tell you about the science that I have had the pleasure of pursuing while at Northwestern through the years, the past 10 years, actually going a little bit further back. Again, we're not going to cover everything, but we're going to hit, of course, some of the most famous discoveries that you've all heard about. And at the end, I'll be happy to answer questions. So let me get started with what is CIERA about? And there it is, this name that's long and nobody wants to say, but we all love the acronym, right? So J, I'm gonna go off script because that's what we do, Morty, right? So the name actually, we were playing, it's not due to me. We were playing, a few of us, my inaugural co-directors, Dave Meyer, whom I see there, Fred Razio, who's out of time, giving another lecture at Cornell today, myself, and one of our interdisciplinary colleagues at the time and collaborators, Bill Kath from Applied Math. And we were playing with words, and I think at the end it was Bill Kath who got the acronym, CIERA. And then we played with the words and we decided to stick to CIERA, and then we had to find the right words. It had to have center, and we knew it had to have astrophysics and interdisciplinary. And then the exploration has a backstory that's too long for tonight. So there it is. What is CIERA about? Of course, at the core of our mission is research. We are a research center at the university, and research is what drives a lot of what we do with our students, our postdoctoral fellows within CIERA, who are really, it's the life, the blood of CIERA is our postdoctoral fellows who come and bring new life to our center every few years, and the faculty. And the kind of research we pursue, it covers all of astronomy, and it's research that covers the universe across all scales, from the smallest things, smallest for us, the planets and the solar system, to the stars. That's the next step in scale. So we care about the life and death of stars. The death of stars gives rise to compact objects, and we're going to have this. There it is. Maybe I have to point there. We had this problem in rehearsal. Death of stars gives rise to corpses, dead stars. They are the exciting black holes and neutron stars that we're going to talk about. And then we care about what happens when you put together lots of stars or dead remnants. And we look at stellar populations and what happens with their dynamical evolution when you have them together. We're going to have trouble with this one. Okay, there we are. Okay, there we are. And then beyond the collection of stars in small clusters, you go to the scale of galaxies. And for galaxies also we study how galaxies are actually formed and evolve throughout the universe. And that takes us to cosmological questions about the whole universe and its origins. And eventually, all of this we study with a lot of electromagnetic astronomy, the standard astronomy we've known for a whole, for several centuries now. But of course, we specialize also in this new era of astronomy that has opened up with the detection of gravitational waves and this new type of astronomy, multi-messenger astronomy. So in the talk, there's no way I'm going to cover all the work CIERA does in all these topics, but we're going to be able to talk about life and death of stars, compact objects, and we're going to cover gravitational waves and multi-messenger astronomy. Okay? Now, how we do this work actually involves a number of interdisciplinary research methods, and that's where our interdisciplinary component comes from. Our focus is on astrophysics research, and that's what our primary mission lies on. But astrophysics, to be pursued, requires knowledge and innovation in many other disciplines, and we need collaboration with many other disciplines. So we pursue our research questions with observations and analysis of data. We pursue it with theoretical simulations, and I'm going to ask for my other clicker to come, or new batteries. We pursue it with theoretical simulations and high-performance computers, and also with building of instrumentation, because we need actual telescopes. Can I use it now? I can speak with that. because we need to have the right detectors to get the signals from the astrophysical sources, to have data to analyze and compare to theoretical simulations. And when we do this work, like Jay mentioned, we collaborate with applied mathematicians, computer scientists, engineers, planetary scientists. I know I'm forgetting some of my collaborators and they're gonna get upset. And of course, the methods we developed, for example, in data analysis, have applications in other fields. Obstetrics was one of the fields where our data analysis was useful, and that's how I teamed up with Teresa Woodruff, for example, for a while, and she became a CIERA member. So this is how we do our research, but it turns out we soon realized, thank you, that apart from our core mission of research, it became inevitable that our drive and our interests expanded well beyond research. So first of all, a lot of what we do, whether it's in theory or in observations, deals with data. The data could be actual data from telescopes, or it could be simulation data produced by supercomputers. But we have to analyze data, and through this data analysis, we are basically training ourselves and our young students and postdoctoral fellows in data analysis, at the forefront of data analysis. So we are feeding into the careers and methodology of data science. So a lot of what we do is data science. And if you're training young people, basically you're STEM educating. And very quickly we realized we had an interest in STEM education all the way to K through 12. So we coupled and started collaborating with education faculty here at Northwestern. We developed an interest in how we build leadership skills for our young researchers. And of course, from the beginning, we had a clear mission that our science is done not just by us, for us, but it's done for society, okay? So public outreach and making sure that we can communicate with you is definitely part of our mission as part of CIERA. So beyond this core, we have all kinds of programs and sub-goals that we pursue that I will not go into any detail. For research, you saw already some of these key images. For all the other goals, there's actual programs that we pursue. These are not just words on a schematic. These are actual programs where people put time and effort, and we're pursuing them with real engagement with the right people at the university or in the local community or at the national scale. So we have data science training, and of course we need high-performance supercomputers. We run a lot of K through 12 education programs, very much aligned and connected to Great University, Good Neighbor Great University program that our President Shapiro initiated some years back. We also think that leadership, whether it's women or minorities especially, but any leadership skills for our young scientists are important for their career development. So professional development is really important. And I won't go into the details of these programs. There's so much to say here, and I'm dying to tell you about them, but I won't be able to do it. And then, of course, public outreach, from involving citizens into actual science to opening our Dearborn Observatory on campus to events like today. I'll mention a couple of things about our STEM education effort. K through 12, again, multiple programs, some funded federally, some funded through philanthropy. But over the 10 years, we have now reached 200 schools, 300 teachers, and almost 5,000 students. We also invest in summer undergraduate research, not only undergraduates at Northwestern, but also from local community colleges and other universities, small undergraduate institutions minority serving institutions in our community, and we involve them also not only in research, but also in other avenues for STEM education. And also in graduate education, we have now developed in data science professional development opportunities for 200 graduate students. And in outreach, you are at one of these events, we'll come back to this, but every week, our Dearborn Observatory is open for free, every Friday night, by reservation or just walk in. And you can come in and meet our graduate students who are there and ask them about what's going on the sky. Graduate students from CIERA and the Department of Physics and Astronomy have collaborated with our talented musicians at Northwestern and have organized arts and science events. Whenever there's something interesting on the sky, we look up. We go to bars. I never go to bars. Deny. And then over 10 years, we have organized 170 public events and have reached out to dozens of thousands of people in our local community. Okay? So this is well beyond research, but it's the research that drives the excitement. We talk about what we do in our daily life. The news that get to the newspapers and the news that don't get to the newspapers. And of course, the annual public lecture is the highlight of our public activity, once a year. Now, for 10 years, we bring external speakers. That's what we do. I have never given a full-hour lecture at Northwestern before. I go to other places and I give these lectures almost once a month, or sometimes twice a month. So I have an outreach committee, and every year we select who the speaker should be. Over the years, we're starting again. There they are. We have hosted Nobel Prize winners, Neil deGrasse Tyson, astronauts, authors. We have had a lot of fun with hosting great speakers. This year, my outreach committee came and said it's our 10th anniversary, and it's you who should give the talk and talk about CIERA. And I told Dave Meyer, he's sitting there, and I said, I don't want to do this. And he said, you're not leaving my office until you say yes. Or something along these lines. So for the 10th anniversary, we decided to highlight CIERA itself instead of having an external speaker. But you know, I'm not going to do this more than once in a decade. So tonight, I can't tell you about all the research that's going on in CIERA, but I will tell you about the kind of research I have had the pleasure to be involved with my students and postdocs and collaborators. I will mention fellow faculty here at Northwestern and try and paint this picture of this amazing new astronomy, the Northwestern astronomy, and the new type of astronomy that we have had the pleasure to open up in the last few years. But it connects to how stars live and die, and how black holes get born and lead to cosmic explosions, but that emit eventually gravitational waves, but also electromagnetic waves, and what are we learning in the past 3 years. A tremendous transformation for our field that we are thrilled, I don't know what word to use, we are beyond amazed to have the opportunity to actually experience. Because when you start your studies and you decide at some point in your life you're going to do academic research for the rest of your life, you don't do this for this kind of discovery. It's everyday pleasure that you get from your teaching and your research and solving, you know, seeing a simple plot that looks like nothing to most people and it gives you great pleasure. This discovery doesn't happen, you know, you can't count on it. It doesn't happen. There's no guarantee you're going to experience it. The fact that we get to experience it now is a great gift. So, we're going to start with stars. Stars, like people, get born out of gas, live their lives, they spend their fuel, and eventually they die. And small stars, like our star, like our sun is an average star, is going to live its life about 9 billion years, and eventually it's going to become a compact object we refer to as a white dwarf. And we're not going to talk much about it or at all for the rest of the talk. And more massive stars that are 10 times the mass of the sun or even more massive, they spend their lives and eventually explode in a supernova, very powerful explosions, but not the most powerful, and eventually will form things that we call neutron stars or black holes. So, let's look a little closer. And we're going to look a little closer to what happens to a massive star. This is a star of about 10 times the mass of the sun. And we're going to follow its life through its time. And you won't see it very clearly, but these are millions of years, the time axis. And these circles around are telling you how big the star is. And this is about 20 times, this circle here is 20 times the size of our sun. And initially, not much is happening. A star is sort of stable, it's bluish, a massive star like this. It's kind of hot and small, but compared to what will happen to it later in its life. So as time progresses, it actually runs out of fuel, of hydrogen in its center, and starts burning higher and higher, heavier and heavier elements in its center, and it becomes bigger and bigger because it becomes hotter in the center and cooler on the outside. Cooler means that it becomes redder on the outside. Intuitive, that may not make any sense, but if you've taken freshman physics, then it makes sense. So eventually, it goes to 10, it's going to reach 10 million years or so. It's going to stick around as a red giant for a while. Has my movie stopped? Yeah. My movie has stopped. By the way, this movie was made here at Northwestern. And it never stopped when I played it anywhere else in the country. So it keeps evolving, and eventually it explodes. And it explodes because basically, and I won't be able to explain this in real detail, but it runs out of nuclear fuel in the center. Gravity makes it collapse in the center. The energy that gets released from the center pushes the outer layers away, so you get an explosion of the outer layers. At the end, you get a black hole, so you can't see it, it's black. And it's a tiny little remnant. And if the sun was a black hole, it would only be 4 miles across. So the whole mass of the sun would be compressed into just 4 miles. So the black holes are the most the most compact objects that exist in the universe, because they represent the ultimate win of gravity, okay? Everything has collapsed in the center. So black holes are stellar remnants, and it turns out that stars actually most often don't live by themselves like our sun, but actually find themselves in binary systems. They have companions, they're in pairs. They live their lives with another star. I was about to say with another person. But when they form, so the first star may have formed a black hole, it's behind its companion now. They're not very good neighbors once they become black holes. They start pulling the matter of their neighbor, and they accrete, they eat basically, they cannibalize their companion. And as the matter falls into the black hole, you get a lot of hot gas surrounding the black hole. You cannot see the black hole, but we knew for decades, since the late 60s, that there must be black holes in the universe because we could see these jets you saw earlier in the movie as X-ray sources. And somewhere here, I'm gonna get, there it is. So this matter accretion onto the black hole emits X-rays. So we had an inkling that black holes exist in the universe, not because we saw gravitational waves before, but because we were detecting X-rays through matter accretion. So that's an important thing to keep in mind. Now, the other type of compact object we knew about indirectly through another type of electromagnetic waves was actually neutron stars, which is what you get to form if you are not a very massive star where gravity wins altogether, but you're a little less massive and gravity gets a worthy opponent. Neutrons, some of the subatomic particles we know of, actually manage to create a ball of themselves, and the pressure of neutrons can resist the gravity of the mass and create a stable compact object called Neutron Star. So if you take 1.5 mass of the sun and you put it in a ball of neutrons, not regular gas, then it's just about 20 miles across. And if you take that neutron star of 1.5 mass times the mass of the sun, and you ask how big is 20 miles across, well, it's about downtown Chicago. And that's how it would look if it was hanging above Chicago. So this image was also created by our IT visualization team. And it was, and it's to scale. This would be the curvature of a neutron star if it were hanging above downtown Chicago. It was used, this image, to, for the press conference Jay mentioned. Two of our images, actually, different institutions created images and graphics, and two of our images were used at the National Press Conference. And this image was at the top article in the New York Times the day of the press conference. So the New York Times had to show downtown Chicago on their cover. Okay. Now, neutron stars. We actually knew neutron stars exist, again, not because of gravitational waves, but because it turns out neutron stars behave as radio lighthouses. So exactly like a lighthouse, neutron stars actually have radio beams, and they emit radio waves. Why they emit radio waves is not for tonight, but they emit radio waves, and every time that crosses our line of sight, we get a pulse of radio waves. So we knew the existence of neutron stars through radio observations, electromagnetic observations. They were discovered by Jocelyn Bell-Bernard. At the time, she was a graduate student in England, and this is how she looks now, and she actually visited Northwestern a couple of years ago. Thanks to one of the CIERA astronomy faculty here at Northwestern, who organizes a lecture series in radio astronomy. So what's the point of what I have said in the last few minutes? The point is the following. We knew about the existence of black holes and neutron stars for a few decades now, late 60s, early 70s. But we had indirect knowledge. It was through X-rays, through radio waves, and these are both electromagnetic waves. And we basically knew about the presence of compact objects in nature through electromagnetic astronomy, which of course, in different wavelengths, which of course developed beyond the optical, beyond the visible, in the previous century. So up until the beginning of the previous century, we only had optical observations of the universe. First with our eye, then with regular telescopes. And then in the previous century, from the early 30s to the late 70s, we opened up the full spectrum, electromagnetic spectrum, because we were able to build all kinds of telescopes. Optical at the tops of mountains, now we have access to some of them. It's not easy to get access to some of them, Morty knows. And in space, built by space agencies in the US and around the world, radio telescopes, and we were able to make observations of the universe from the highest energies gamma rays to the lowest energies radio with detectors that eventually entered our regular life. And you don't realize how much of the technology we use in our regular life, from medical to everyday, like the microwave ovens, actually the detectors were developed because astronomers were pushing the technology and pushing for innovation in telescopes, and then the detectors actually entered, airport security, night vision goggles, etc., etc. So there's a lot of applications of electromagnetic light detectors that has been pushed, tag and, what's the expression, I'm going to get it wrong, but between applications either in the military, medicine, or other security applications, but often it has been pushed by NASA or ground-based astronomy first, and then applied into everyday life. All right. So that's where we were and what we knew about compact objects, especially black holes and neutron stars, up until around 2015. We knew they existed. We also knew, I'm going to get to that, we also knew that another type of waves existed in nature called gravitational waves. But what happened on September 14, 2015, just about 3 years ago, is that we actually managed to detect for the first time this new type of waves called gravitational waves that we had never directly detected before from a cosmic source or from any other source, actually. And that opened up a completely new astronomy era. It's like, and I'm going to make this analog again later, it's like we only had optical astronomy, and then we started having gamma ray and radio and infrared, etc. And this probably doesn't sound as dramatic to you as it sounds to me as an astronomer. So let me make another analogy. It's like going from silent movies to the movies we have now with sound. Gravitational waves and gravitational wave telescopes operate a little bit like our ears instead of our eyes. So it's like going from being able to just see the universe to also be able to see and hear the universe. How transformative was that transition in the movies for our culture, for our way of thinking, for literature, for, just think about it. This is what we're living through in astronomy. This is what's happening since 2015 in the scientific community. And this is why it's such a big deal. Okay, so binary, so what did we see on September 14, 2015? Well, we heard gravitational waves from a pair of of black holes. So let me tell you a little bit now more about what are gravitational waves. So, a little tutorial on general relativity. Do you have anywhere to go for the rest of the and how the detectors work, etc., etc. Okay, so maybe one slide on gravitational waves. So, electromagnetic waves are oscillations of electric and magnetic fields. If you've never heard of this, it's okay, that's not the time to, process this. But any wave is an oscillation of something. Okay? Gravitational waves is an oscillation of something. The question is, of what? It's not of electric and magnetic fields. Gravitational waves is an oscillation of space-time. Okay. Now, this is a direct consequence of Einstein's theory of general relativity. And I'm going to show you a little movie also made by one of our Northwestern graduate students who's now a postdoctoral fellow at MIT. And I'll try to give you a sense of what gravitational waves are, and we're gonna leave it at that. So gravitational waves, as I said, are oscillations of space-time. We're gonna only think about oscillations in space, because that's a little easier. And we're gonna think about space as a two-dimensional thing, okay, not a three-dimensional thing. So, Einstein thought about gravity in a completely different way, and he envisioned and then proved that basically mass distorts the geometry of space. Space is not flat the way we experience it around us, but actually any mass curves space, and bigger masses curve space even more. The dimples are deeper. And if those masses are actually now moving and accelerating themselves, then the dimples in space are moving, and they're disturbing the space, and those disturbances are not static in place, but actually generate waves. And all of that falls out of the math of the theory of general relativity. And this is how it looks. You have two black holes, one is yellow, the other is blue. They're going one around the other, and the dimples, you can see how they're distorting the geometry of space. And as they're accelerating, one is static in this movie, the other is going around the yellow. And this acceleration of the dimples is basically disturbs space, and the waves get generated by this motion of the two black holes, or any bodies to be true. And the waves propagate away from this pair of two compact objects, okay? Now, in reality, any two masses do that. As I do my two arms, as I move them this way, I generate gravitational waves. But they are inconsequential. The oscillation I cause is minuscule, okay? No detector could ever detect it. So the way to think about gravitational waves is that they are easier to think about them as space ripples, the ripples you saw. But these are the oscillations. Okay, and I'll come back to the question, did we have any inkling that gravitational waves existed? They fall out of the math, but there's tons of things that fall out of math, okay, mathematical theories. Not everything that comes out of a mathematical theory actually is natural, all right? So we know that, as physicists, we know that. We tell the mathematicians all the time. So for a long time, it wasn't clear that these gravitational waves existed in nature. And the way we got real indirect proof that gravitational waves existed was back in the 70s, crazy decade, when, back to radio waves, these two guys, graduate student and advisor, at UMass Amherst, they discovered a pair of neutron stars. One of them was a radio lighthouse. They started studying the radio pulses, and they realized that these two neutron stars were coming closer over 10 years. So they didn't realize it in a month, okay? So they monitored for 10 years, kind of boring work. And they realized that this orbit was coming closer and closer together, not by, I don't know, billions of kilometers, by, I don't remember now the numbers, but centimeters over billions of kilometers. And they were able to measure this. It turns out this shrinkage of that orbit was consistent with Einstein's prediction that gravitational waves must be emitted. And gravitational waves, like any wave, like electromagnetic waves, are carrying energy away from the motion of these two objects. And if they're losing energy, then the two objects are coming closer and closer together. So we were able to have indirect evidence through a precise measurement in radio waves that gravitational waves must exist. So then, in the 70s, people started saying, this is not just a mathematical theory. These waves exist. And if waves exist, like electromagnetic waves, we want to do astronomy with them. So a few people started thinking, especially Ray Weiss, who eventually I became a mentor of mine, started talking with Kip Thorne, who's a theoretical astrophysicist who only wanted to understand black holes on computers. Started talking to each other. Ray Weiss, a complete experimentalist, who had the attitude that I don't give a damn what the theorists are telling me. If I cannot measure it, I don't believe it. So they started talking to each other, and he wanted to basically figure out a way to detect gravitational waves. They built on pre-existing work, and eventually Ray came with the idea that laser interferometry was the way to detect gravitational waves. There's a movie here. I know there's a movie here. There. So you can send down lasers, you can split them in two beams in an L shape, send them down to mirrors, bring them back as they reflect from the mirrors, and analyze the pattern, the interferometry pattern. If a wave comes down, a gravitational wave comes down, then the space is not static. It's oscillating in a very particular way, in a stretching and squeezing kind of way, if the wave is coming from a pair of black holes at some distance in the cosmos. They did the calculations, and they figured out what kind of instrument you need to build. Barry Barish joined the project at some point and made it happen, made it a real project. And eventually we got to 2015. But I'm rushing the story because really this started in the early 70s. So it took basically close to 50 years to get to the detection, okay? Talking about long, persistent work with zero detections, getting the instrument to work. That was where all the effort was. And here's how they look now. These are the gravitational wave telescopes. They don't look like telescopes, right? But they work. And there is a third one now that lives in Italy, and the Europeans built it, and it joined us 2 years later, 2017, it started working with us. Now the question is, how much of a stretching and squeezing those mirrors are undergoing when two black holes somewhere in the universe are colliding, moving one around the other, coming closer and closer together? Well, the number is a small number, 10 to the minus 18 meters. What does this mean to you? Not much. Doesn't mean much to me either. When I throw these numbers away, astronomers throw these numbers away, really big ones, really small ones, nanoscientists also throw these numbers away. Let me tell you how small this number is. Okay, you start with a meter, which is basically about 3 feet. What is that? About this big. Okay? Then you divide it, I went too fast. You divide it by 10,000, a factor of 10,000, you get the thickness of your human hair. You divide it by another factor of 100, you get the wavelength of optical light. You divide it by another factor of 10,000, you get to how big an atom is. You divide it by another factor of 1,000, I think is coming, 100,000 of course. And each time you divide by another factor of the previous one, not the very first one, you get to a nucleus. And then you divide it by another factor of 1,000 because what the heck? Because that's what you need to get to 10 to the minus 18. That's how small the amplitude of the wave is. Okay? This is not something that will make your face go up and down and up and down. And there it is. That's what we got in the laser pattern on 2015, September 14, a gravitational wave from a binary black hole, and we'll get to that. And this is how it looked. The space, we measured that the mirrors were moving up and down, and the frequency of the evolution was increasing. We'll talk about that in a minute. We figured out, using Einstein's theory of general relativity, that the pair of black holes that created this signal actually collided over 1 billion years ago. So the event happened over 1 billion light years away. Okay? Think about this a little bit. Longer than life has existed on the Earth. When the collision of the two black holes happened, energy was released in gravitational waves, not in light. But if you take that energy, that power, the whole signal lasted 0.2 seconds, roughly. The signal in our detector, 0.2 seconds. If you take the energy released in those 0.2 seconds and you calculate the power in gravitational waves, that power, if you convert it into optical light, which is not, but if you convert it, was 50 times brighter than all the stars in the universe. Not the stars our eyes see if we were somewhere really dark, but all the stars that exist in the universe for those 0.2 seconds. The energy that was released was 3 million times more than we would need if we ever wanted to destroy our sun. Not that we would. The final black hole was about 62 solar masses. And it was about, I can't do it by my hands, but it was about 200 miles across, the width of the Illinois state. Okay? Tiny, much smaller than the Earth. Very compact. And the two black holes, right before they touched each other, they were moving by about 60% of the speed of light, which is 1/3 billion miles per hour. Kind of fast for your teenager. So with the data, we were able to extract all this information using Einstein's theory of general relativity and build these computer simulations. These are the two black holes emitting their gravitational waves and coming closer and closer together. As they come closer and closer together, they're stirring space-time more and more vigorous. So the amplitude of the wave goes up. And they eventually merge because they're losing energy from their orbit. They're touching each other and they merge into a single black hole, which eventually settles. And there's no motion anymore. There's no acceleration anymore. There's a single black hole. It's no longer a pair. And everything quiets down, including the space. And then there's no more gravitational waves. So the signal ends. So we start, we get the oscillations in our detectors. As the black holes come closer and closer, swirling together, closer and closer like the figure skater, the amplitude, the disturbance in space becomes more vigorous, and the frequency of the wave, the peaks come closer and closer together. The pitch, if it were a sound, becomes higher and higher, and then the wave dies down. So this is what we observed. We call this the gravitational wave chirp, because if you convert the gravitational waves into sound waves, they sound like a chirp, a bird chirp. So let's hear it. Okay, the first version is the real version. The frequencies of gravitational waves that our detectors can detect vary from about 50 hertz to 500 hertz right now. 400 hertz is the node A. So if we play the signal exactly in the frequencies it came in gravitational waves and we convert it into sound, it's the first version, which is kind of a thump, thump, and our ear doesn't hear it very well. So the second version is just shifted a little bit to higher frequencies so our ear can catch it. So it is shifted to higher frequencies and we get this, it gets louder and the pitch gets higher, okay? So we talk about gravitational waves as being sounds, and please do not leave this lecture thinking Professor Kalogera said gravitational waves are sounds, okay? They're not sounds. But the frequencies are similar to sounds. And there is a real analogy that is important. The detectors, the gravitational wave telescopes, act as ears. Our eyes can only see what we're looking at, what we're pointing at, like optical telescopes, okay? But the gravitational waves telescopes, the L-shaped things, they can detect gravitational waves from all kinds of directions, like our ears. I can hear sounds from under me, behind me, but I cannot see anything unless I'm pointing at it, okay? So there's a difference between the ear and the eye, and the telescopes, the gravitational wave telescopes, act more like ears than eyes. So that's why we like the sound analogy. All right. So this is what we received in the data. This is another way to look at it. Frequency as a function of time. The frequency went up and then it ended. And the amplitude of the wave, the brightness in this banana, goes up because the vigorousness of hooking up or messing up the space-time as they were merging goes up. The little thin curved line here is actually a prediction based on Einstein's theory of general relativity. And you can see that it follows based on what we understand from the theory, it follows the data. So we confirmed that basically it's the first time we test Einstein's theory at this regime where objects are moving at half the speed of light. We have never had the opportunity to directly test whether his theory works at this highly dynamic, disturbed space-time environment. Now, what are we doing with these gravitational waves? Apart from this one event, we now have about 6 events that we have announced. And we are trying to understand how pairs of black holes form. We're trying to understand how the astrophysics works. In my group, we study them in terms of how isolated pairs of black holes can form. In another colleague's faculty here at Northwestern, they study black holes in dense stellar environments. This is another simulation and visualization produced here at Northwestern. So I'm gonna ask Shane. Where is Shane? What time is it?
6.
Exactly 6. Okay, that's what I thought. I'm gonna try and take just 5 minutes and tell you about the multi-messenger discovery. Okay? So we talked about pairs of black holes. Now we're gonna talk about pairs of neutron stars, where basically 2 years later, almost 2 years later, we received a different kind of signal. In the gravitational wave telescopes, we received gravitational waves, of course, that's all we can receive. But the signal looked slightly different. It looked, again, a chirp, except this time it lasted for tens of seconds. Here you see 30 seconds. It has this curved increasing frequency as a function of time, and then it ends. In our detectors, it lasted for 100 plus seconds instead of 0.2 seconds or 1 second that the black holes last. 2 seconds after the gravitational wave signal ended, colleagues of ours with a gamma ray, working with a gamma ray satellite in orbit around the Earth received a signal in gamma rays. Now I know this doesn't look like anything to you, but to gamma ray astronomers, this is a signal. And they know their statistics. And they could tell immediately. They sent an alert, in fact, before we realized we had a signal. And they sent an alert and they said, we have a gamma ray signal somewhere there on the sky. And then we said, we have a gravitational wave signal somewhere around the same area in the sky. And it was the first time that we had both gamma rays and gravitational waves coming from the same area in the sky. And within 2 hours, with more analysis that was happening on the spot, communicating, sending tons of emails, texts, etc., we were realizing, we were narrowing down the area of the sky and realizing that for the first time in the history of astronomy, we had a single source that was emitting, had emitted, because the signals ended in 2 seconds, had emitted gravitational waves and gamma rays. The first multi-messenger source in the history of astronomy with gravitational waves. Okay, there we are. That started this first detection of gamma rays and gravitational waves, then immediately alerted the whole astronomy community. And we had faculty, thankfully, and in fact, not just faculty, but postdoctoral fellows also at CIERA, who were involved on the electromagnetic side as well, and launched the whole campaign across the full electromagnetic spectrum, and found the source also in the optical that initially looked blue on the same night. We had to wait for the night to come down in the southern hemisphere, and 4 days later it looked reddish. The projector doesn't show, but it's reddish on my screen. And by analyzing the optical data, we knew from theoretical astrophysics that it had the signatures of gold and platinum actually formation, and that was the emission we were seeing. So this was a discovery of a pair of neutron stars going through the same dance the black holes were doing, producing initially only gravitational waves. And this dance lasted a lot longer in the gravitational wave detectors. They were going one around the other, messing up space-time and producing gravitational waves, ripples, sending us relatively close by, not 1 billion light years away, only 130 million light years away, in a nearby galaxy by astronomy standards, a galaxy called NGC 4933. Eventually, the two neutron stars collided one next to each other, and then the electromagnetic fireworks started. We got the gamma rays in these jets, and then eventually we got optical light and gold and platinum formation in the center here. And at Northwestern, my group was studying the gravitational waves, and we had two other faculty, faculty who were just hired in the last 2 years, who were studying the electromagnetic signature of this source, this historic multi-messenger source. So here they are, because science is not done without people, so I like to show photos. This is our now gravitational wave group. Shane Larson is a colleague also, faculty. Rafaela Marguti and Wen Fei Fong are the two junior faculty on the electromagnetic side, studying, collaborating all together on the study of this double neutron star collision with their team members. And she's sitting right here, a graduate student, because actually she works on both sides. And I'm sure she has her legs on both sides. I will say, now I'm taking a little bit of extra time, but I will say that in this discovery that I had the pleasure of participating at the National Press Conference representing the LIGO collaboration. The LIGO collaboration is more than 1,000 people. It was 3 of us representing the whole collaboration in the key prime press conference. Caltech, MIT, and Northwestern. And but in terms of the multi-messenger, we were the only university, since it's homecoming, I can brag about us, right? We were the only university in the country that actually led publications, both on the gravitational wave side and on the electromagnetic side, from the same university. Most universities were either leading on the gravitational wave side only, or on the electromagnetic side only. But thanks to our vision to really go after this area of astronomy, we had faculty leading on both sides. So as Jay said, he mentioned Discover, Breakthrough, the multi-messenger discovery. The year before, the binary black hole discoveries, only gravitational waves, were also deemed Breakthrough of the Year. Science, all of science, Breakthrough of the Year in 2016. Now we try to understand black holes and neutron stars and how they formed. There's tons of questions that got opened up. I'm telling you about the answers and how we discovered and understood how these things work, but there's actually tons of questions and things we don't understand. We don't know what happened when the two neutron stars actually collided. There's a question mark here. There's this gap in masses between neutron stars and black holes. We don't know why the LIGO black holes are all up there, separate from the X-ray black holes. So there's a lot of things we don't understand, which gives us job security. Waiting for 2019, the detectors are coming online. There it is. This is torturing me. 2019 and beyond, the detectors right now, the gravitational wave detectors, are not operating. They're undergoing an upgrade, and they're going to come up in 2019 more sensitive, which means we're going to increase the rate at which we detect these things. The expectation is that once they reach the targeted sensitivity in 2019, we're expecting 1 to a few, we're not certain, binary black hole detections per week, and maybe optimistically, one double neutron star detection per month. So I don't know how much sleep we'll be getting, but there's a lot of work ahead of us. If you're curious to engage with this particular area, look up Gravity Spy and help us hunt for gravitational waves. Also, look up our Media LIGO webpage, or look up the science blog Shane Larson, my CIERA associate director, is writing. I lost him, he's back there. There's a lot of information you can find on our website and learn more about this. And I will end by saying that we have a lot of other things going on within CIERA. You can join us on Facebook, Twitter, any other social media. If you want to help us out or engage with our events, our public events, join our email list. Look up our CIERA Circle. If you want to find out our fantastic board of visitors, then email me or CIERA@northwestern.edu. We're celebrating our 10 years. I can't believe 10 years have passed. We can't wait what we're gonna see and hear in the next 10 years. Thank you so much.
Okay, so thank you everyone. Those of you who have